Hello viewers, I am Asghar Pasha, Assistant Professor, Department of Mathematics, MS Ramaya Institute of Technology, Bangalore. In this session, I will continue solving problems on first order higher degree differential equations which are solvable for y. Problem number 4. Find the general and singular solution of y plus px equals to x to the power of 4 into p square. The procedure of solving equations which are solvable for y is differentiate with respect to x, then extract the factor containing derivative from it, which involves p x, which is a first order differential equation in p and x. You solve that differential equation to get p, substitute that p value in the equation to get a relationship between y and x involving one arbitrary constant, which is general solution of a given differential equation. In this case, y is y equals to minus px plus x to the power of 4 into p square. I will differentiate this equation with respect to x to get dy by dx equals to product rule here, minus p into derivative of x is 1. Second function x to minus x into derivative of p with respect to x is dp by dx plus derivative of next term, which is x power of 4 into p square, is 4x cube, derivative of first function treating second function as constant, plus x to the power of 4 as it is, derivative of p square is 2p into dp by dx. We know that dy by dx is p, so p equals to minus p minus x dp by dx plus 4x cube p square as it is plus 2x to the power of p into dp by dx. Shift minus p to LHS as well as minus x dp by dx to LHS to get 2p plus x into dp by dx equals to 4x cube into p square plus 2x to the power of 4 into p dp by dx. Next step, it is 2p plus x dp by dx equals to 2xp into 2p plus x into dp by dx. Transfer 2x cube p into 2p plus x dp by dx to left hand side to get 2p into 2p plus x dp by dx minus 2x cube p into 2p plus x dp by dx equals to 0. Now collect 2p plus x dp by dx term to get 1 minus 2xp equals to 0. So this is a term containing a derivative term. This is free from derivatives. So from the first factor, if you equate first factor to 0, you will get general solution. And from the second one, 1 minus 2x cube p equals to 0, you get singular solution. So for general solution, consider 2p plus x into dp by dx equals to 0. Now you have to solve this differential equation, which is linear in p and x. We can write this as x into dp by dx equals to minus 2p. Separate the variables. You can write this as dp by p equals to minus 2 dx by x. Variables are separated here. You integrate it to get p in terms of x involving one arbitrary constant c. Integrate it. We get log p equals to, which is integration of 1 by p, minus 2 times log x plus some arbitrary constant which I have taken as log c. Now law of indices, logarithms, minus 2 into log x can be written as log of x to the power of minus 2. So log p is log of x power of minus 2 plus log c. Next line, log p equals to log of, now log a plus log b is log of a into b, which implies p equals to c into x power of minus 2. Therefore, p is c divided by x square. Substitute this p value in the given equation and eliminate p to get y as minus c by x plus c square. This is the required general solution. Now, To get a singular solution, we have to consider the another factor, which is 1 minus 2x cube p equals to 0. We can find singular solution from the general solution also. General solution is y equals to minus c by x plus c square. If we differentiate this with respect to c, treating y and x as constant, and then eliminate c from that equation and the general solution, we get a relation between y and x involving no constant, which is a singular solution of the differential equation. The other method is equating the another factor to 0. 1 minus 2x cube p equals to 0, which implies p equals to 1 divided by 2x cube. Now substitute this value in the given differential equation. Given differential equation is y plus px equals to x power of 4 into p square. You substitute p as 1 by 2x cube to get y plus p into x equals to x to the power of 4 into p square. P is 1 by 2x cube. So y plus 1 by 2x square, cancel 1x here. So y plus 1 divided by 2x square equals to x to the power of 4 into 1 divided by square of 2x cube, which is 4x to the power of 6. After simplification, you get it as y plus 1 by 2x square equals to 1 divided by 4x square, which implies y equals to minus 1 divided by 4x square. Now method 2 of getting this singular solution from the general solution. You can see the general solution of this differential equation is y equals to minus c by x plus c square. Now if I differentiate this equation with respect to c, treating x and y as constant, we get 0 here, derivative of y is 0, that is equals to minus 1 by x, constant, derivative of c is 1 plus c square. Derivative of c square is 2c. Therefore, 2c is 1 by x, which is nothing but c equals to 1 divided by 2x. What I have done here, I have differentiated the general solution with respect to arbitrary constant c, treating y and x as constant. Derivative of y is 0, that is equals to minus 1 by x, derivative of c is 1 plus derivative of c square is 2c. With this 2c becomes 1 by x, so c is 1 by 2x. Now you have to substitute the c value in the general solution. So if you substitute here, you get y equals to minus c by x. C is 1 by 2x, so it is minus 1 divided by 2x. 2x into x is 2x square plus c square. C square is 1 by 4x square. Now simplify this. Y equals to, it's minus 1 by 2 plus 1 by 4. You simplify this, you will get minus 1 by 4x square as solution, which is singular solution of this differential equation. You can see that this is true even in this case. Y equals to minus 1 by 4x square. Now let us move on to the next problem. Problem number 5. Obtain general and singular solution of the equation y equals to p sin p plus cos p. The given differential equation is y equals to p sin p plus cos p. Differentiate this equation with respect to x to get dy by dx equals to, now product rule here, p as it is, derivative of sin p is cos p into dp by dx plus sin p. Second function as it is, derivative of first function is dp by dx minus, or which is the derivative of cos p. Derivative of cos p is minus sin p into dp by dx. Cancel plus sin p dp by dx minus sin p dp by dx, and write dy by dx as p to get p equals to p times cos p into dp by dx, which is nothing but 1 equals to, cancel p, 1 equals to cos p into dp by dx. So I have even if you consider this as p minus p into cos p into dp by dx equals to 0. So we have p into 1 minus cos p into dp by dx equals to 0. So one factor, I am equating this to 0, which is 1 equals to cos p into dp by dx. The previous slide, from the previous slide we have 1 equals to cos p into dp by dx. We have to solve this equation. This is linear in p, it is a linear differential equation in p and x. We can easily solve this by separating the variables. Separate x and p to get dx equals to cos p into dp. Now integrate this to get x equals to sin p plus c. So sin p is x minus c, which in turn implies p is sin inverse of x minus c. Now we have to substitute this value in the given differential equation to get this equation, y equals to sin inverse of x minus c, which is p. This is p into sin of p plus cos of p. This value is p, sin inverse of x minus c. So the general solution of the given differential equation is y equals to, I have written this term first, sin of sin inverse of x minus c is x minus c. This is as it is, sin inverse of x minus c plus, next term is cos of sin inverse of x minus c, which is the required general solution of the given differential equation. Of course, if you want singular solution of that differential equation, you eliminate c here by differentiating this with respect to c and then substitute back in the general solution to get a relationship between y and x. Problem number 6, obtain the general solution and the singular solution of the equation xp square minus 2yp plus x equals to 0. Now the given differential equation is xp square minus 2yp plus x equals to 0. Now I will solve this for y and write in this form. You can transfer this to RHS and express this equation in terms of y as y equals to 1 plus p square into x divided by 2p. Now differentiate this equation with respect to x. We get dy by dx equals to 2p into product quotient rule we have to apply, and then internally we have product rule because denominator and denominator we have 2p and the numerator contains product of two terms 1 plus p square into x. So we have to differentiate that using product rule. On a whole, first we have to apply quotient rule, that is denominator into derivative of numerator, for which we have to apply product rule. Dy by dx equals to denominator, this 2p is denominator. Now this is derivative of 1 plus p square into x. Derivative of 1 plus p square into x with respect to x. First function 1 plus p square as it is, derivative of x is 1 plus second function x as it is. Now derivative of 1 plus p square, derivative of 1 is 0, derivative of p square is 2p times dp by dx minus numerator is 1 plus p square into x, derivative of denominator is 2p, derivative of 2p is 2 times dp by dx, whole divided by 4p square, denominator square. Now you simplify this, multiply by 2p into 1 2p plus 2p cube, multiply 2p to the third term which makes it 4x p square into dp by dx minus, you simplify this, 2x into 1 2x, 2x into dp by dx minus 2x p square into dp by dx divided by 4p square. Multiply throughout by 4p square to get 4p cube equals to 2p plus 2p cube. You simplify these two terms. From third and fifth term we have this one, 2x p square into dp by dx, this term as it is, minus 2x into dp by dx. When you transfer this term to LHS, we get 4p cube minus 2p cube as 2p cube equals to 2p as it is, plus in these two terms take 2x and dp by dx common to get 2x into p square minus 1 into dp by dx. So, which implies 2p cube minus 2p equals to 2x into p square minus 1 into dp by dx. Now, take 2p common here, 2p into p square minus 1 equals to 2x into p square minus 1 dp by dx. Okay, I have arrived at this stage after simplifying this. Take this to left hand side, we get 2p into p square minus 1 minus 2x into p square minus 1 dp by dx equals to 0. So, in these two things, two terms, 2, it's not p, 2 common, p square minus p common, p square minus 1 is common, take 2 into p square minus 1 outside, p is left here, minus x into, I have taken p square minus 1 outside, dp by dx equals to 0. Yes, I have two factors here, one p square minus 1, another one p minus x into dp by p minus x into dp by dx equal to 0. If I equate this to 0, I will get general solution and this leads to singular solution. Now, equate p minus x into dp by dx equal to 0. If we equate this to 0, we get p as x into dp by dx. You solve this by separating the variables dx by x. Simplify this to get dx by x equals to dp by p. Now, variables are in separable form. Its solution can be obtained by integrating it directly. Integrate it. Integration of 1 by x is log x, integration of 1 by p is log p, plus some constant of integration which is log c. So, after using properties of logarithms, we get x equals to pc, which in turn implies p equals to x by c. Now, substitute this value of p in the given equation. So, when you substitute this p value here, x into p square minus 2y into p plus x equals to 0, and simplify this, we get x square minus 2cy plus c square equals to 0, which is general solution of the given differential equation. We have seen there was a factor of this type, 2 into p square minus 1 equals to 0. You can obtain singular solution from this factor also, but the method 2 is, when we have general solution, you differentiate that with respect to arbitrary constant, treating x and y as constants. Now, let me differentiate 2 with respect to c. Derivative of x square is 0, minus 2cy, minus 2y is constant, derivative of c is 1, so it is only minus 2y, plus derivative of c square is 2c, which implies c equals to y. Now, substitute c equals to y in equation 2, we get x square minus, in place of c it is y, y into y square, so it is minus 2y square plus y square equal to 0. Finally, we have x square minus y square equals to 0, which is singular solution of this differential equation. Now, as I said earlier, there was one more factor, p square minus 1 equals to 0. So from this factor, if we equate this to 0, we get p square equals to 1. You can get a singular solution by substituting p square equals to 1 here in the given differential equation. P square is 1. If you want, you can square the equation to avoid imaginary value of p here. You can square this given differential equation. You can take this to right hand side to have even powers of p. I will show this to you. P square is 1. So what you can do is, to have only even powers of p, I will take 2yp to right hand side. So it is xp square plus x equals to 2yp. If I square it, I will get x square into p square, p to the power of 4, plus second function x square plus 2ab. 2 into ab, it is x square into p square equals to derivative of square of 2yb is 4y square into p square, and the factor was p square minus 1. So when you equate that to 0, p square becomes 1. So you substitute here, it is x square into p to the power of 4. P square is 1, so p to the power of 4 is also 1, plus x square here, plus p square is 1, so it is 2x square, plus p square is 1, it's not plus, it is equals to 4y square into p square is 1. Okay. You add all these things, x square plus 2x square is 4x square equals to 4y square, which implies x square minus y square equals to 0. So this x square minus y square equals to 0 is a singular solution of this differential equation. X square minus y square equals to 0. You can see here, yes, we have x square minus I'll just show that to you. Problem number 6. Yes, you can see the singular solution is x square minus y square equals to 0, which we have obtained by differentiating the general solution. Differentiating the general solution, x square minus 2cy plus c square equals to 0 with respect to arbitrary constant c, treating x and y as constants. Okay, the same equation, x square minus y square equal to 0, we obtain the same equation by equating the other factor p square minus 1 equals to 0. Now, let me summarize this. So far I discussed solution of first order non-differential equation, first order non-linear differential equation first order non-linear differential equation. What do you mean by non-linear differential equation? Differential equation, of course, having higher degree terms. First order non-linear differential equation by three techniques. One, equations solvable for p. Second one, equations solvable for y. and then equations solvable for x. Now how to solve this? How to use solve for p technique? You know, it will be in the form of p to the power of n, some function of x and y into p to the power of n minus 1 and so on. It can be treated as a polynomial in p. You just find the factors like p minus f1 into p minus f2 dot p minus fn equals to 0. When you equate this, each factor p minus f1 equals to 0, p minus fi equals to 0, which is a linear differential equation. P is dy by dx minus f1 equals to 0. f1 is a function of x and y. This is a linear differential equation. You can easily solve this differential equation by known techniques, maybe a variable separable form or exact differential form or homogeneous type, or else using integrating factor concept. So you can solve this to get solution y equals to f1 of x comma c involving one arbitrary constant. Similarly, consider p minus f2. P minus f2, equate that to 0. P minus f2 equal to 0 implies dy by dx minus f2 equals to 0. Again a linear differential equation y and x. Solve that equation by known techniques to get one more solution y equals to some capital F1. This is capital F1, capital F2 of x comma c equal to 0, and so on. So you get n solution. If degree is n, you will be having n factors, which is nothing but you will get n linear differential equations of first order. You solve them to get n solutions, and product of these n solutions along with one arbitrary constant c constitutes general solution of that differential equation. This is solvable for p. Next, solvable for x. If equation is solvable for x, you can write that equation as x equals to some function of p and y. Now you have to differentiate this equation with respect to y. Dx by dy equal to, you differentiate it to get some function of p, y and dp by dy. You call this dx by dy as 1 by p, because p is dy by dx, and then you simplify this to get solution of some differential equation of this type. You get p in terms of y and c, substitute this value in the given differential equation and eliminate p to get the required general solution. The same concept with respect to y. If the equation is solvable for y, then you can write that as y equals to some function of x and p. You differentiate this with respect to x, you will get an equation involving p and y. You solve that and then substitute the value of p in this differential in the given differential equation, and after elimination of p, the p eliminant of this equation gives general solution of the equation. Now, is it possible to solve a given problem in all the three techniques or not? Let me take one example. I will show you. I will apply all these three techniques to solve that equation. Consider xp square plus x equals to 2y into p. Now method number 1, I will try to solve this using solving for p. Now I have to factorize this. It's like xp square, it's a quadratic equation in p. Xp square minus 2yp plus x equals to 0. So roots are p equals to minus b, which is plus 2, minus b, which is plus 2y, plus or minus root of b square. B square is 4y square, b square minus 4ac. 4ac is 4 into x, 4x square divided by 2a. A is x divided by 2x. Now simplify this. This is 2y plus or minus, take 4 outside to get 2 times root of y square minus x square divided by 2x. So what is p here? P is divided by 2, cancel 2 here to get y plus or minus root of y square minus x square divided by x. So we have 2 factors here. We have to solve this. I'll consider one factor. P equals to y plus square root of y square minus x square divided by x. Now what is P? P is dy by dx. dy by dx equals to y plus root of y square minus x square divided by x. Now we have to solve this differential equation. I cannot separate the variables. You can see this is a homogeneous differential equation. Degree of denominator is 1, degree of numerator. Of course, all terms are 1 because y square and x square are under root. It's a homogeneous differential equation. We can find its solution by using the substitution y by x equals to some new variable v, or y equals to v into x. I'll call this as equation 1. I'm using the substitution y equals to vx to solve this equation 1. I'll differentiate y with respect to x. Derivative of y is dy by dx equals to, now v is a new variable which is a function of x. We have to apply product rule here. First function v as it is, v into derivative of x is 1 plus second function x, derivative of v is dv by dx. V plus x into dv by dx. Now I have to substitute this equation 2 and 3 in 1. With this substitution, equation 1 reduces to an equation with equation which is in separable form, which will be in separable form, means we can separate the variables, independent and dependent variables. Let me substitute this in 1. Okay. LHS is dy by dx. dy by dx is v plus x into dv by dx. I have substituted for dy by dx, and that is equals to y plus square root of, okay, if you want you can substitute y in terms of v. Y is vx plus root of y square. Y square is v square into x square minus x square divided by denominator x. So I have converted everything in terms of v and x. So we have to simplify this. Now it's v plus x into dv by dx equals to, separate it, it is vx by x plus, I'll take x square outside, so it becomes x into root of v square minus 1 divided by x. Now cancel x, I can cancel this x here, and we will be left with v plus x into dv by dx equals to v only, v plus root of v square minus 1. Cancel v, we get x into dv by dx equals to root of v square minus 1. Now, next step, separate the variables. You can write this equation as dv divided by square root of v square minus 1, that is equals to dx divided by x. Now, you have to integrate it. It is root of x square minus 1, and you know that integration of 1 by square root of x square minus 1 is a cos hyperbolic inverse of x. So, this part is cos hyperbolic inverse of v, that is equals to dx by x. Integration of 1 by x is log x plus some arbitrary constant c. If you don't want to write this in terms of cos hyperbolic inverse, you can use the alternate formula. Alternate formula is like this: integration of 1 by square root of x square minus 1 dx equals to log of x plus root of x square minus 1. So, this is more appropriate here because I have log c, log x, and even this c can be written as log c. So, I can cancel log throughout. So, I will not use cos hyperbolic inverse v formula here. I will express dx by root of v square minus 1 in terms of log. The alternate formula, integration of 1 by root of v square minus 1 is log of v plus root of v square minus 1, and that is equals to integration of 1 by x is log x plus some arbitrary constant log c. So, use properties of logarithms. You write this log x plus log c as log of x into c, and cancel log on both the sides to get v plus v square minus 1 equals to x into c. Now, substitute for v. We have assumed that y equals to, or y by x equals to v. This was our assumption, the substitution what we made to convert that homogeneous differential equation into an equation in variable separable form. So, you substitute this value here. V is y by x plus root of v square, y square by x square minus 1 equals to x into c. Now, you simplify this equation, y square by x square minus 1 okay. I will simplify this. It is y by x plus, you take LCM, this is x square, this becomes root of y square minus x square divided by x square equals to x into c. So, which in turn becomes y by x plus square root of y square minus x square divided by x equals to xc. Now, multiply throughout by x to get y plus root of y square minus x square equals to x square into c. So, this is one solution. Similarly, by considering one more factor, one more possibility, you get homogeneous equation again. Use the same procedure of converting that into variable separable form and arrive at one more solution. Product of these two solutions serves as a general solution of the differential equation. So, this is solvable for P. Now, how to solve this using solvable for X technique? The differential equation was xp square plus x equals to 2 into y into p. if you take x common here, it is x into p square plus 1 equals to 2yp. Therefore, x equals to 2yp divided by p square plus 1. This is, I have expressed this equation in terms of x. You have to differentiate this equation with respect to y, or else you can differentiate the given this one only. If you want to avoid quotient rule, you differentiate xp square plus x equals to 2yp with respect to y. If I differentiate it, product rule, I am differentiating this with respect to y. X into derivative of p square is 2p into dp by dy plus second function p square into derivative of x with respect to y is dx by dy. So, I have differentiated the first term. This x into 2p dp by dy plus p square into dx by dy is derivative of xp square, plus we have x, derivative of x with respect to y is dx by dy, and that is equals to, now product rule, 2y into derivative of p with respect to y is dp by dy plus 2p as it is, derivative of y is 1. Now, you simplify this equation. Okay. Consider, you have to write this dx by dy as 1 by p. So, you have to convert, basically you have to convert this in terms of p and y only. So, I can get rid of this dx by dy terms. You can write this as 1 by p, no doubt about it. But the problem is with this x term, we have x, but already we have an equation for x here, x equals to 2yp divided by p square plus 1. You just substitute that x value. So, we get, in place of x, if I write 2yp divided by p square plus 1 into remaining term as it is 2p into dp by dy plus p square into dx by dy is 1 by p. Let me erase this. Now, plus I have written this term p square into 1 by p. Now, you can write this dx by dy as 1 by p equals to RHS. RHS is 2y into dp by dy plus 2p. Now, simplify this. We need a factor involving dp by dy. First term is 4y into p square divided by p square plus 1 into dp by dy. Second term, p square into 1 by p is p plus 1 by p as it is, and this is equals to 2y into dp by dy plus 2p. Now, I will shift this term to LHS, which makes it 4yp square into p square plus 1 into dp by dy minus, when you transfer this to LHS, this becomes 2y into dp by dy equals to, you shift these terms, these two terms to RHS, p plus 1 by p to RHS, we get 2p minus p minus 1 by p. Now, solve this, simplify this. Okay. I'll erase this. Consider, yes, I'll take in these two terms, you can see 2 is common, y is common, dp by dy is common. So if you take 2y into dp by dy outside, you will be left with 2p square divided by p square plus 1 minus 1. This is LHS, because 2y into 2p square is 4y p squared by p square plus 1 as it is, and I have taken 2y dp by dy outside, so it is 1. That is equals to RHS. 2p minus p is p, so it is only p minus 1 by p. Simplify this. What we get? 2y into dp by dy into, take LCM, LCM is p square, 2p square minus p square minus 1 divided by p square plus 1 equals to, again, p minus 1 by p can be written as p square minus 1 divided by p. Simplify this. This is 2y into dp by dy into 2p square minus p square is p square minus 1 divided by p square plus 1 equals to p square minus 1 divided by p. Now simplify this. We have two factors here involving p square minus 1, so I can take it out to get a factor involving derivative term dp by dy term. Take this to left hand side, multiply by p, you get 2yp into dp by dy into p square minus 1 divided by p square plus 1 minus of p square minus 1 equals to 0. Now in these two terms, p square minus 1 is common, and you will be left with 2yp divided by p square plus 1 into dp by dy minus 1 equals to 0. So there are two factors, one is p square minus 1 equal to 0, another one is 2yp divided by p square plus 1 into dp by dy minus 1 equals to 0. As I said earlier, this p square minus 1 equals to 0 leads to singular solution. For general solution, we have to equate the factor involving dp by dy to 0. So let me equate this to 0. So when you equate this factor to 0, we get 2yp divided by p square plus 1 dp by dy equals to 1. Now we have to solve this differential equation. Using variable separable technique, you can separate it easily. Separate the variables. You can write this equation as cross multiply. You transfer y terms to RHS. You will be left with 2p divided by p square plus 1 into dp, that is equals to dy divided by y. So this 2p and p square plus 1 remains in the LHS, and you just cross multiply dy and y to get 2p by p square plus 1 into dp equals to dy by y. Next, it is in separable form. Its solution can be obtained by direct integration. You can see I have to integrate this to get the solution. Denominator, this denominator p square plus 1 and numerator 2p, it's of the form f dash of p by f of p. That is, numerator is derivative of denominator, and you know that integration of f dash of x by f of x dx equals to log of f of x. 2p is derivative of p square plus 1, so I can directly integrate it. You can write this as log of p square plus 1 equals to integration of 1 by y is log y plus some arbitrary constant, I will write that in terms of log c. So this implies you can write this log y plus log c as log cy, which makes p square plus 1 equals to cy. Therefore, p square is cy minus 1. Now we have to substitute this p value in the given differential equation and eliminate p. Of course, when you substitute p here, it gets eliminated in terms of it will be expressed in terms of y. So final answer will contain only x and y with one arbitrary constant c. That is the general solution of the differential equation. Similarly, equations solvable for y. The same technique can be employed to solve this equation in terms of y. Let me take the example xp square plus x equals to 2yp. You can express this in terms of y as y equals to xp square plus x divided by 2p. I have expressed this in terms of y. Now we have to differentiate the third type now. To get solution, we have to differentiate y with respect to x. I can do that here only using quotient rule, or else I can differentiate here and then replace y term by xp square plus x by 2p as usual. So it is also solvable for pi. You can try it and use the same technique as I have explained. Today I solved 4 problems on equations solvable for y. The same type it is. You can use that technique, solve this equation, eliminate p and get the general solution. If singular solution is required, you differentiate general solution with respect to arbitrary constant, or else you equate the other factor which is free from derivatives to 0 and get the singular solution. So this is about solution of nonlinear differential equation of first order. We discussed 3 cases. So in the next class, in the next session, I will discuss a special type of nonlinear differential equation known as Clairaut's equation. Thank you.